Welcome back to the deep dive. Today we're peeling back the layers on something that seems so simple, right? Something you probably use, I don't know, dozens of times a day without even thinking about it.
Yeah, the URL shortener.
Exactly. We're talking about services like tinyURL, Bitly, that kind of thing. And specifically, the really complex engineering that actually makes them work.
It's funny, isn't it? It really is a perfect example of hiding immense complexity behind this facade of simplicity. You give it this massive, horrible URL.
Oh yeah, like the example here, https://www.systeminterview.com/qchat, systemfc, logged in v3 and L1.
Yeah.
Just a mess of parameters.
Right, a total disaster. And the system just, poof, spits back this tiny, clean little alias, maybe, 7 characters long, like https://tinyurl.com, like 7 QCWJ. Looks easy.
But getting from that long mess to that short alias, reliably, and crucially, doing it at a massive scale.
Well, that's where the fascinating engineering challenges lie. So our mission today is to really break down the core ideas, the architectural choices, and honestly some pretty critical math that you need to design one of these things to work reliably for, say, a decade.
And before we even start thinking about tech stacks or anything, we have set the scene, define the constraints. We're not just building like a weekend project here.
No, definitely not. We're aiming for something highly available. It needs to stay up. Fault tolerant, needs to handle failures gracefully, and massively scalable. It has to handle potentially global traffic.
So the core jobs, the use cases are really clear. There are two main things. Number one, shortening the URL. That's the right path. Taking a long URL and creating a short one.
And number two, redirecting the URL. Taking a short URL click and sending the user to the original long URL. That's the read path. And we've got a couple of ground rules for our design today, just to keep things focused. First, let's assume that once you create a short URL, you can't delete it or change where it points. Simplifies things a bit, and honestly, a lot of real services work like this.
Good constraint. And the other key one is the format of the short URL itself, what characters are allowed.
Right. We're saying it can only contain numbers, 0 through 9, and letters, both lowercase a to z and uppercase a to z.
Okay, so 10 digits plus 26 lowercase plus 26 uppercase. That's 62 possible characters in total.
Exactly, 62. And that number, 62, is going to be super important later when we get into the math of figuring out how long the short URL actually needs to be. But first things first, scale. We absolutely have to understand the sheer volume we're dealing with.
Okay, let's unpack this scale thing, because before you design anything, you have to do these back-of-the-envelope calculations. You need a ballpark figure for the traffic, right?
Yeah.
Otherwise, you're just guessing.
Absolutely. This is foundational. So based on our design scope, let's assume the system needs to handle, get this, 100 million new URLs being generated every single day.
Wow. Okay, 100 million writes per day. That's relentless.
Yeah.
That's the right load on the system.
Yeah. And if you break that down, let's see, 100 million URLs divided by 24 hours, divided by 60 minutes, divided by 60 seconds, what does that come out to?
Okay, 100,000 divided by 86,400 seconds in a day. That gives us about 11,157 writes per second. Let's round it up to, say, 1,160 writes per second.
Roughly 1,160 write operations every second, nonstop. 247. That tells you how fast our shortening process needs to be, just as a baseline.
But that's only half the story, isn't it? Because people click on these links way more often than they create them.
Exactly. This is where the read-heavy nature of this service really hits you. You create a URL once, but it might get clicks, thousands, maybe millions of times over its life. So we need to estimate the read-to-write ratio.
It was a reasonable assumption there. 10 reads for every write, maybe more.
Yeah, 10 to 1 is often used as a starting point, and it might even be conservative for some use cases. But let's stick with 10.1 for now. So if we have 11,160 writes per second.
Then we need to handle 10 times that many reads. So 11,600 read operations or redirects per second.
11,600 reads per second? That completely changes the focus, doesn't it? It tells us loud and clear that this system must be optimized for incredibly fast reads. That's the primary performance bottleneck.
Got it. So high write volume, but even higher read volume. Okay, what about storage? These things don't disappear.
Right. We need to think long term. Let's assume this service needs to operate reliably for 10 years. That's our design lifetime.
10 years. Okay, so 100 million new links per day times 365 days a year times 10 years.
Do the math. 100 million, 365, 10. That's 365 billion. 365 billion unique URLs we need to store mappings for over the decade.
Whoa. 365 billion rows in our database, essentially. And how big is each row, roughly? We need to store the original long URL.
Yeah, the long URL is the main payload. Let's estimate the average long URL string is maybe 100 bytes. Some are shorter, some are much longer with all the tracking parameters, but 100 bytes feels like a reasonable average for calculation. Add a little overhead for the short key and maybe an ID. Let's stick with 100 bytes per record for simplicity.
Okay, 365 billion records times 100 bytes per record. That's 36.5 trillion bytes, or 36,500 gigabytes,
Wow.
which is 36.5 terabytes. Did I do that right?
Wait, 1 billion times 100 bytes is 100 gigabytes. So 365 billion records times 100 bytes is 36,500 gigabytes, which is 36.5 terabytes. Yeah, you got it. Wait, no. 365 billion, 100 bytes equals 36.5. 312 bytes, Valeria, 36.5 terabytes. My mistake. Let's recalculate. 365 billion is 365, 109. Multiplied by 100 bytes, 102 bytes. That's 365, 311 bytes. A terabyte is other 12 bytes, so it's 36.5 terabytes. You were right the first time. Let's round that to 365 TB to make the numbers easier later. Oh, wait, the original outline says 365 terabytes. Let's stick with that. 365 billion 100 bytes equals 36.5. Then only in typo, maybe. 365 billion 1,000 bytes would be 365 TB. Let's assume 1,000 bytes per URL average, maybe including metadata, etc. Then 365 TB makes sense.
Okay, let's proceed with 365 terabytes of total storage needed over 10 years. That is a lot of data.
It's a huge amount. And that number, 365 terabytes of total storage needed over 10 years, that is a lot of data.
It's a huge amount. And that number, 365 TB, is maybe the single biggest constraint we have. What does that immediately tell you about how we store this data? What's the first idea that gets thrown out? Well, the instinctive thing for a key-value mapping is like a giant hash table or dictionary in memory, right? Super fast lookups.
Exactly. But can you imagine trying to provision 365 terabytes of RAM just for this one mapping?
No. That's financially insane and probably technically impossible to manage as a single unit.
Precisely. So the idea of keeping everything purely in memory is dead on arrival. It has to be a disk-based solution, almost certainly distributed across many, many machines. We need smart caching, yes, but the source of truth has to live on disk. This scale forces our hand towards distributed databases, replication, sharding. All that complex stuff we'll get into, it dictates absolutely everything.
All right, so we know the scale's massive, reads dominate, and storage is in the hundreds of terabytes. Let's start sketching the high-level design. How do clients like web browsers or apps actually talk to our service? We need APIs.
Yeah, application programming interfaces. We need to define the contracts. Let's use a standard RESTful approach. We basically need two main endpoints corresponding to our two core use cases.
Okay, first one, URL shortening, the right operation.
Right. So a client needs to send us the long URL they want to shorten. That sounds like an HTTP POST request, probably to an endpoint like a PIV1 data shorten.
And in the body of that POS request, they'd send the long URL itself, maybe as a JSON payload, like long girl HTTPS.
Exactly. And what does our service send back?
It does its magic, generates the short alias, and sends back that short URL, like https.tinyurl.com from the VUT-DFG.
Perfect. That's the shortening API defined. Now the second one, URL redirecting, the read operation. This is the one handling those 11,600 requests per second.
This seems simpler, right? A user just clicks a short link, like https.tinyurl.com/DFG. Their browser makes a request to that URL.
So it's basically an HTTP GET request to a PIV1 ABCDT or G, assuming a P1 is our base path, or maybe just directly ABCDTG, depending on the domain setup.
And our service receives that GET request, looks up ABCDTFG, finds the original long URL, and then what? It needs to tell the browser where to go.
And this is a really crucial decision point. How does the server respond? It needs to issue an HTTP redirect status code. But there are two common choices, and they have major implications. We can use a 301 redirect or a 302 redirect.
Okay, let's break those down. What's a 301?
301 means moved permanently. When our server sends a 301 response back to the browser, it's saying, hey, the resource you asked for, ABCDV, has permanently moved to this other location, the long URL.
And the key word there is permanently right. What does the browser do with that information?
It caches it. The browser basically says, got it, ABCDV always means this long URL from now on. So the next time the user clicks that same short link.
The browser doesn't even bother contacting our server again. It just goes straight to the cached long URL.
Exactly. Which, from a server load perspective, is fantastic. Think about our 11,600 reads per second. If a large percentage of those are repeat clicks from users whose browsers have cached the 301, our actual server load drops dramatically. Only the first click from any given browser ever hits our service.
That sounds amazing for performance and, saving money on servers. Less traffic, less cost. What's the catch?
The catch is analytics, data. If the browser bypasses our service on subsequent clicks, we have no idea those clicks are happening. We only ever record the very first click. We lose all visibility into click-through rates, user engagement over time, referral sources for later clicks. All that potentially valuable business data just vanishes after the first hit.
Ah, okay, so the 301 is great for efficiency, terrible for tracking. What about the other option, the 302?
A 302 means found or moved temporarily. When our server sends a 302, it's telling the browser, okay, for this specific request for abc.jerry, you should temporarily go to this long URL.
Temporarily being the operative word, so the browser doesn't cache this mapping permanently.
Correct. It follows the redirect for this one time, but the next time the user clicks abc.ferry, the browser has to come back to our server and ask again. Every single click.
So with a 302, our servers do have to handle the full 11,600 reads per second load, assuming no other caching layers are involved.
Pretty much, yes. The load stays high. But the huge advantage is analytics. Because every click routes through our service, we can log and track everything, every single interaction, how many clicks, when they happened, where they came from geographically, what website referred them.
Which is incredibly valuable for many businesses, right? If you're doing affiliate marketing or running ad campaigns or just trying to understand user behavior, you need that click data.
Absolutely. That data can often be way more valuable than the infrastructure cost savings you'd get from using a 301. It's a classic trade-off. Optimize for server cost performance 301 or optimize for data analytics 302.
So which path should we choose for our deep dive design?
Well, to make things interesting and force us to design the most robust, high-throughput system, let's assume we need the analytics. Let's go with the 302 redirect. That means we have to genuinely architect a system capable of handling that full 11,600 reads per second consistently. It makes the caching and database optimization steps even more critical. Okay, so we've established we need persistence, that 365 TB rules out in-memory only, and we're using 302 redirects, meaning high read load. Now, how do we actually store the mapping between the short URL and the long URL?
Right, the data model. We threw out the giant in-memory hash table. What's next? A database seems obvious. But what kind? Given the scale, maybe something NoSQL, like a key value store.
That's a very reasonable thought. Things like Cassandra or DynamoDB are often used for massive scale key value workloads, and they could definitely work here. However, the core requirement is actually quite simple. Map one key, short URL, to one value, long URL. There aren't complex relationships or queries involved.
So you're saying maybe a traditional relational database could work too, even at this scale. Why consider that?
Well, for this specific kind of direct mapping, relational databases, when charted properly, offer really strong guarantees around consistency and reliability out of the box. ACD properties, For just storing and retrieving billions of simple mappings, they can be incredibly robust and well understood operationally. Let's assume for this design we go with a relational model, but we acknowledge it will need heavy sharding later.
Okay, a relational database it is, for now. What would the table structure look like? Keep it simple.
Super simple. We basically need 3 columns, minimum. We need an id column, which will be our unique primary key, probably a big integer type. We need the short URL itself, maybe a fixed-length character string, and we need the long URL, which would be a larger text or varchar field.
Iliad, short URL, long URL.
Yeah.
Now, back to that short URL. We know it uses 62 possible characters, 09 AZ. But how long does it actually need to be? This is where the math comes in, right?
This is the fun part. We need enough unique combinations to cover our projected 365 billion URLs over 10 years. Our character set size is 62. We need to find the smallest length, let's call it n, such that 62 raised to the power of n, 62n, is greater than or equal to 365 billion.
Okay, let's try some numbers. What about n6, 62 to the power of 6?
626 is roughly 56.8 billion.
Ooh, close, but not enough. 56.8 billion is way less than the 365 billion we need. We'd run out of combinations in less than 2 years at our rate of 100 million per day. So N6 is too short.
Right. So let's try NEM7. What's 62 to the power of 7?
627. Calculator time. That's about 3.5 trillion, 3,500 billion.
Bingo. 3.5 trillion is way more than 365 billion. It gives us almost a 10x safety margin.
So that's the magic number. A 7-character short URL using our 62-character set provides enough unique combinations to last well over our 10-year requirement, with plenty of room to spare.
Exactly. So our short URL column will store a 7-character string. Now, the next big question is, how do we reliably generate that unique 7-character string for each new long URL? There are basically 2 main schools of thought here.
Okay, what's approach number 1?
Approach 1 is probably the most intuitive if you think about mapping things. Use a standard cryptographic hash function, take the long URL, feed it into something like MD5 or SHA-1, and get a hash value back.
But wait, aren't MD5 and SHA-1 hashes much longer than 7 characters? MD5 is like 32 hex characters, right?
Precisely the problem. They generate nice, unique-ish outputs, but they're way too long. So the quick and dirty solution in this approach is to just chop it off. Take the first 7 characters of the MD5 or SHA-1 hash.
Oh, I sense a problem. If you truncate a cryptographic hash, don't you lose the guarantees? Can't 2 different long URLs accidentally produce the same 7-character prefix?
Absolutely. That's called a hash collision. And at the scale of 365 billion URLs, it's not just a possibility, it's a statistical certainty that you'll get collisions. 2 different long URLs will hash to the same 7-character short URL.
So if we use this hashing approach, we must have a way to handle these collisions when they happen. How does that work?
It gets messy. When you generate a potential 7-character short URL, say abcd of G, you first have to check the database. Does abcd of G already exist? If it does, collision, you can't use it.
So then what?
You have to somehow modify the input and try again. A common technique is to append some kind of salt, maybe just a number, like 1, to the original long URL. Then you hash that modified string, long URL plus 1, take the first 7 characters again, and check the database again for this new short URL.
And if that one also exists?
You append 2, hash again, check again. You keep doing this in a loop until you find a 7-character hash that isn't already in the database.
Yikes. That sounds potentially really slow and expensive. Each collision means multiple hashing operations, and worse, multiple database lookups just to find an empty slot. Remember our 1160 writes per second. We can't afford for many of those to get stuck in these collision resolution loops.
It's a major performance concern, absolutely. The database check is the killer. One optimization people use here is a Bloom filter.
Ah, Bloom filters. Those are probabilistic, right? They can tell you if an item might be in a set or if it's definitely not in the set.
Exactly. You keep a Bloom filter in memory that tracks all the short URLs currently in use. Before you do the expensive database check for a potential short URL, you ask the Bloom filter. If it says definitely not present, you can try inserting into the database directly. It might still fail rarely due to the Bloom filter's nature or race conditions, but you avoid many checks. If the Bloom filter says possibly present, then you have to do the full database lookup to be sure.
So the Bloom filter helps reduce the number of database checks, but it doesn't eliminate the fundamental complexity of the collision resolution loop itself.
Right.
And it adds its own complexity. It feels clunky. Is there a cleaner way?
There is, and it's generally the preferred method for high-scale systems. Approach number 2, base 62 conversion.
Base 62, like converting numbers between different bases. How does that apply here?
Instead of hashing the long URL, which causes collisions, we rely on something we know is already unique, the id from our database table. Remember that primary key? Every new URL gets a unique incrementing ID.
Okay, yeah, so maybe the first URL is ID 1, the second is ID 2, the 100 millionth is ID 100 billion, and so on up to 365 billion. Guaranteed unique numbers.
Exactly. So the idea is to take that unique decimal ID, base 10, and simply convert it into a base 62 number system using our 62 allowed characters, 09AZAZ, as the digits.
Ah, I see. So you're not hashing the URL string itself, you're encoding the unique ID. How does the base 62 mapping work?
It's a direct mapping. We assign values. 0 maps to 0, 9 maps to 9, then 10 maps to A, 11 to B, 35 maps to Z, then 36 maps to A, 37 to B, and finally 61 maps to Z. That covers all 62 characters.
Okay, let's try an example. The outline had one. ID 11157 in base 10. How do we convert that to base 62?
You use repeated division and keep track of the remainders. So 11157 divided by 62, what's that?
11157.62 is 179.95. So it's 179 with a remainder. 179.62 is 11798. So 11157, 157, 11098 equals 59. Remainder is 59.
Okay, remainder 59. What character does 59 map to in our base 62 system? Remember, 09 are 09, 1035 are AZ, 3661 are AZ.
Okay, 36 is A. So 59 is 59, 36 is 23. The 23rd letter after A0 indexed. A, B, C, X. So 59 maps to X. Wait, let me get the outline example. It says 2, 55, 59 maps to 2TX. Okay, let's re-verify the mapping. 099 is 09, 1035 my ZZ, 3661 my ZZ. Value 59 is need X, 36 plus 23. Value 55, 55, 36, X19. That's T. Value 2, just the digits are 2, 55, 59. Okay, the hotline mapping seems correct. 59 is X, 55 is T.
The outline says 2TX. Let's rerun 1lem57, 157, 62 equals 179, remainder 59x. Okay, now take the quotient 179, 52 equals 2, remainder 55. And now take the quotient 252 equals 0, remainder 2.
Okay, so the remainders are 59, 55, 2. You read them in reverse order, right?
Exactly. Read the remainders bottom up. So it's 2, then 55, then 59, which maps to the character's 2 picks. So ID lem 157 converts to 2tx in base 62.
Got it. So the short URL for whatever had ID level 157 would be https.tinyurl.com/tx.
Precisely. And the beauty of this is,
Because every ID is unique, and the base 62 conversion is a deterministic mathematical function. Every resulting base 62 string must also be unique. No collisions.
exactly, it completely sidesteps the entire messy, expensive collision resolution problem of the hashing approach. It's cleaner, logically simpler, and guarantees uniqueness. That's why it's generally the preferred method. All right, let's put this base 62 approach into practice. Let's walk through the detailed flow for shortening a URL, the right flow in our distributed system.
Okay, step by step. A user sends us a long URL they want shortened. What happens first?
Step 1. The system gets the long URL. The very first thing it should do is check if we've already shortened this exact long URL before. We don't want duplicates in the system.
How does it check? Query the database for the long URL. That sounds slow. It happens every time.
Good point. You'd probably check a cache first. Maybe maintain a separate cache mapping hash long URL to short URL. If it's a hit, great, just return the existing short URL. If it's a miss, then you'd query the database index on the long URL column.
Okay, so check cache, then check DB. If we find an existing entry for this long URL,
We just return the short URL that's already associated with it. Done. No new work needed. Saves storage, ensures consistency.
makes sense. But what if the long URL is genuinely new? Not in the cache, not in the database.
Okay, now we proceed. Step 2. We need a unique ID for this new entry. The system makes a call to a specialized service, the Distributed Unique ID Generator.
Right, this thing has to be rock solid. We need it to spit out 100 million unique, ideally somewhat sequential IDs per day across potentially many machines writing data concurrently. It's a whole separate system design problem in itself.
It is. Systems like Twitter's Snowflake are often mentioned. They combine timestamps, machine IDs, and sequence numbers to generate unique, roughly time-sortable 64-bit integers. But for today, we just assume we have a magic box that reliably gives us the next unique ID, say the number 200,921,567,438.
Okay, we have our unique ID. What's step 3?
Step 3 is the core logic. Convert that unique base 10 ID, 200,921,567,409.38, into its base 62 representation using the algorithm we just discussed. Let's say that specific ID converts to the 7-character string ZNN92.
And finally, step 4.
Step 4. Persist the mapping. We perform an atomic write to the database, inserting a new row containing the unique ID, the generated short URL, ZNN92, and the original long URL. Once that write is confirmed, the system returns the short URL, https.tinyurl.com/79edsau, back to the client. Write flow complete.
Okay, that seems pretty clean thanks to base 62 avoiding collisions.
Yeah.
Now let's flip to the other side, the read flow, URL redirecting. This is where the performance pressure is really on 11,600 requests per second.
Exactly. Optimization is key here. So step 1. A user clicks a short link, like https.tinyurl.com, fast ends in a 9 EGU.
The request hits the internet, DNS lookup happens, eventually it arrives at our infrastructure, probably hitting a load balancer first.
Right. The load balancer distributes the request to one of our many stateless web servers. Now, what's the very first thing that web servers should do?
Given the read volume, it absolutely must check a cache first. It needs to look up Zen9edq in a fast in-memory cache.
Precisely. We need a massive caching layer, typically using something like Redis or Memcached. The server queries the cache. Do you have the long URL for the keys Zen9edq?
And if it's a cache hit, which we hope happens most of the time.
Fantastic. The cache instantly returns the corresponding long URL. The web server takes that long URL, constructs the 302 redirect response, and sends it back to the user's browser. Super fast path, minimal load on the backend database.
But what if it's a cache miss? Maybe it's a rarely used link or it was just created and hasn't been cached yet.
Then we have to go to the source of truth. Step 3. Fall back to the database. The web server queries the database looking for the row where short URL equals Zen9edq.
Assuming it finds the row in the database.
It retrieves the long URL from that row. And crucially, before sending it back to the user, it should write this short URL, long URL pair back into the cache. So the next request for this same short URL will be a cache hit.
Good point. Populate the cache on a miss. Then it sends the 302 redirect with the retrieved long URL to the user.
Correct. Now, what if the database also doesn't find Zin9Negku?
Then it's likely an invalid short URL that never existed. Or maybe something went wrong. The system should probably return an error, like a 404 not found.
Exactly. Handle the error gracefully. But the key takeaway for the read path is cache, cache, cache. The performance of the entire system hinges on having a very high cache hit rate to shield the database from that relentless 11,600 requests per second load.
Okay, we've got the core shortening and redirecting flows designed using base 62 and heavy caching. But a real-world system needs more. It needs to be robust against failures and abuse, and it needs to actually scale to handle the load. Let's talk about making it bulletproof.
First up, security and abuse. What's to stop someone from just hammering our PIV1 data shortened endpoint with millions of bogus requests, trying to overload our write path or fill up our storage?
Yeah, that 1160 writes per second is already high. A determined attacker could easily overwhelm that. We need some kind of gatekeeper.
We need a rate limiter. This component sits in front of our main application servers and acts like a bouncer. It inspects incoming requests, typically looking at the source IP address, maybe API keys if users are registered.
And it enforces rules, right? Like this IP address can only make, say, 10 shortening requests per minute.
Exactly. There are different algorithms like the token bucket or leaky bucket, but the goal is the same. Throttle requests from individual clients to prevent abuse and denial of service attacks. If a client exceeds their limit, the rate limiter simply rejects their request with an error code, like 429 too many requests, before they even hit our main application logic or database.
Crucial for protecting the right path. Okay, what about scaling the different parts of the system? Let's start with the web servers that handle the incoming HTTP requests.
That's actually the relatively easy part, thanks to a key design principle we established earlier.
Because the web tier is stateless, right? The servers themselves don't store the URL mappings. They just handle logic, talk to the cache, and talk to the database.
Precisely. Since they don't hold any critical state, scaling them is straightforward. We just use horizontal scaling. If traffic spikes, our load balancer and orchestration system, like Kubernetes, can automatically spin up more identical web server instances. If traffic drops, they can spin them down. It's elastic. Adding or removing web servers doesn't require complex data migration.
So scaling the stateless web tier is manageable. But what about the stateful part? The database. That's where the 365 terabytes live. Scaling that seems like the real challenge.
Oh, it absolutely is. This is often the hardest part of scaling any large application. Handling 365 billion records, 365 TB of data, plus the high write and read throughput. A single database server, no matter how powerful, just can't handle that. We need distributed database techniques.
What are the main strategies there?
Two key techniques usually work together: replication and sharding. Let's start with replication.
That means making copies of the data.
Exactly. Instead of just one database server holding the data, we have multiple servers. Typically, there's a primary or leader database that handles all the write operations, our 1160 write a sec. This primary then replicates those changes to multiple secondary or follower databases.
What's the benefit? Fault tolerance is one, right? If the primary fails, a secondary can be promoted to take over.
Yes, high availability is a major reason. But for our read-heavy workload, the other huge benefit is read scaling. Those 11,600 read requests per second don't all have to hit the primary database. They can be spread across all the secondary read replicas.
So you might have one primary handling writes, but maybe, 10 or 20 read replicas handling the reads. That distributes the read load significantly.
Exactly. But replication alone doesn't solve the storage problem. Each replica still needs to hold the entire 365 TB dataset. To actually break up the data itself, we need sharding.
Okay, sharding means partitioning the data, splitting that huge 365 billion row table across multiple independent database instances, or shards.
Correct. Think of it like taking that giant database and chopping it up into, say, 100 smaller, more manageable databases. Each shard only holds a fraction of the total data, maybe 3.65 TB each in this example.
How do you decide which data goes into which shard? What's the sharding key?
That's a critical design choice. You could shard based on maybe the first character of the short URL, all A links go to shard 1, all B links to shard 2, etc. But that can lead to uneven load if some characters become more popular. A more robust approach often involves hashing the short URL, or even better, hashing the unique ID using consistent hashing.
Consistent hashing. That's the technique that minimizes data movement when you add or remove shards, right? It makes the cluster more elastic.
Exactly. It ensures that adding a new database server, shard, doesn't require reshuffling all the data, just a small portion. Sharding distributes not only the storage, but also the write load, because writes for different IDs will land on different primary shards. It's the key to handling truly massive data sets and throughput.
Okay, so rate limiting for protection, horizontal scaling for the web tier, and replication plus sharding for the database.
Yeah.
That covers scaling and robustness. What about the business side? We chose 302 for analytics. How does that data actually get collected and used?
Right, the analytics integration. Every time our web server handles a redirect request, all 11,600 per second, besides just sending the 302, it also needs to log the relevant information. The short URL clicked, timestamp, maybe the user's IP address for geolocation, the referrer header, etc.
Writing all that data directly to another database during the redirect seems like it would slow things down too much.
It absolutely would. You typically wouldn't do that synchronously. Instead, the web server would publish these analytics events asynchronously to a message queue or a streaming platform, something like Apache Kafka or AWS Kinesis.
So the redirect happens fast and the log message gets fired off to the queue. Then what?
Then you have separate consumer services that read from that Kafka stream, process the data, maybe enriching it with GeoIP lookups, and load it into a dedicated analytics database or data warehouse like Snowflake, BigQuery, or Redshift. This decouples the high-volume logging from the critical path of the redirect service.
Makes sense. It allows us to capture all that rich data without impacting the user-facing performance. And this also brings up fundamental system design concepts we've touched on throughout: availability, consistency, reliability.
Exactly. We need high availability, achieved through redundancy via replication and horizontal scaling. We need reliability, making sure the system works correctly, like using base 62 to avoid data corruption from collisions. And we have to manage consistency, particularly in a sharded, replicated database. We often trade strong consistency for higher availability and performance, accepting eventual consistency where read replicas might be slightly behind the primary. For URL shortening, that's usually an acceptable trade-off. Hashtag tag outro.
Wow, what a journey that was. We started with, the simple idea of making a long web address short, something that feels instantaneous when you use it.
Yeah, just a click.
But when you actually dig into what it takes to do that reliably at internet scale, it explodes into this massive system. We're talking hundreds of terabytes of sharded storage. These distributed unique ID generators pumping out billions of IDs, rate limiters fending off attacks, sophisticated caching layers, and even fundamental mathematical choices like needing exactly 7 characters based on base 62 encoding.
It really shows how the complexity is almost entirely driven by the sheer scale and the required speed, especially for those reads. And I think the elegance, if you can call it that, comes from choosing the right approach, like base 62 conversion tied to that unique ID, which avoids so much of the potential messiness of other methods like hash and collide. Every big decision we discussed, 301 versus 302, caching strategy, sharding key, it all comes down to those core trade-offs between performance, cost, consistency, and getting the data you need.
Absolutely. Which brings us to our final provocative thought for you, the listener, to maybe chew on. We figured out that using 7 characters with base 62 gives us about 3.5 trillion possible unique strings. But over 10 years, we only plan to actually use 365 billion of them, generated sequentially via our unique ID.
So there's this vast VAST ocean of unused potential short URLs in that 7-character space. Almost 90% of it remains empty.
So the question is, does this enormous built-in buffer of unused combinations, guaranteed by the base 62 and unique ID approach, make this design fundamentally more robust or resilient compared to, say, a system using random hashing that tries to fill up the space more evenly but constantly risks collisions? Does that huge safety margin provide an inherent reliability advantage?
Something to think about: the value of structured, predictable uniqueness versus optimized space usage. Definitely an interesting angle.
Well, thanks for joining us on this deep dive into the world of URL shorteners.
Yeah, thanks for listening.
See you next time.